4.4 is about the mean value theorem. We're going to talk about Rawls' theorem, which leads us to the mean value theorem. And as long as you recognize these patterns, you're going to find this section is pretty good, okay? So first, let's talk about what Rawls' theorem says. If we have a continuous function on some interval from A to B, including A and B, if f is differentiable, it doesn't have to be differentiable on the ends, but it does have to be differentiable everywhere in between. So it can't have any discontinuities, it can't have any pointy points, it can't have any cusps. It has to be a nice smooth curve from A to B. Now, if the endpoints match, so again, top three things it has to have. It is continuous, it is differentiable, and f of A equals f of B. So the endpoints match. Then there exists somewhere within that interval where f of C is equal to 0. The f prime of C, I'm sorry, is equal to 0. So there exists somewhere where the derivative is equal to 0. So write that down, and then we're going to discuss what it means.
We've been over this in this class before. This is
Yeah.
and she's never given us a clear answer. It's your brain. My brain sucks. My brain. If we're not going to use it, why do I need it? My brain. You don't have to remember.
Mathematics is an exercise for your brain, just like lifting weights is an exercise for your body. It makes your brain stronger in everything you do for the rest of your life. So if you open up those synapses now, you will be smarter when making decisions about your farm. You will be smarter when making decisions about whatever you're going to do in life. It's just good for your brain. It's just good for your brain. Gotta build up to it a little bit better then. Okay, so let's take a look at what Rawls' theorem says. So it's got to be continuous. So let's take a look at these functions up here. So you'll see they're nice continuous curves, and the endpoints matches. There's no holes, discontinuities, jumps in the graph. There's no pointy points. There's no cuspy things. There's a spot between A and B where there's a derivative that's equal to 0. There's a spot between A and B where the derivative is equal to 0. The ends match. It's a continuous function. There's somewhere where the first derivative is equal to 0, which means there is a horizontal asymptote at that spot. That means that we are on the search for absolute and local mins and maxes. So Rawls' theorem just guarantees that if a function is continuous on a closed interval, differentiable on an open interval, and the ends match, somewhere there is a first derivative that's equal to 0. So that's what that is saying. That somewhere in that interval, there is a first derivative that's equal to 0. You have to have the ends match, you have to have it continuous, you have to have it differentiable, and then we know that somewhere in there, there's a derivative equal to 0. Now, we know those derivatives equal to 0. Look, derivative 0, derivative 0, derivative 0, derivative 0. All those spots where our derivative is equal to 0 are important. And those are going to give us those critical points. Remember those critical points we were talking about in earlier sections. The critical points are where the first derivative is equal to 0 or is undefined. So here it tells us kind of that we are guaranteed to have one in a particular interval if it matches these three conditions. Okay. So let's use Rawls' theorem to help us find those spots where the first derivative is equal to 0. Okay, so let's take a look at part A. It says for each of the following, verify that the function satisfies the criteria stated in the Rawls theorem, and then find all values C in the interval where f prime of C is equal to 0. So let's start with A. Okay, so we are looking at the interval from -2 to 0. Now, the first thing we want to check is we want to ask ourselves, is it continuous? Well, it's a polynomial. So yes, it's continuous. It's continuous everywhere. Second thing we want to check, is it differentiable? Well, the first derivative is 2x plus 2, which is also continuous, which has no problems. So yes, the second thing holds. The third thing we have to check are, do the ends match? So what is f of -2 and what is f of 0? Because for Rawls' theorem to guarantee that there is some f prime of C within the interval, then we must have the endpoints matching. If you plug -2 into the original function, you get 4 minus 4 or 0. If you plug in 0 into the original function, you get 0 plus 0, which is also 0. So bam, we've got the third thing. So that's how you verify quickly that it satisfies the criteria of Rawls. So it's continuous, it's differentiable, and the endpoints match. Then we can move on to finding the f prime of C. Now, I already did the derivative for you right here. So let's look at, where does 2x plus 2 equal 0? Well, let's solve it. So we get 2x equals -2, x equals -1. Is that in the interval? Yes, it is. Now, there are times where we may find multiple locations where the first derivative equals 0, but maybe one of them is in the interval and one of them is not. It only guarantees that there's at least one, and not all of the ones that we find will be in there. So just make sure it is in the interval. So that's all you have to do. That's it. Okay. Now let's do the same exact thing for B. We're going to do the same three things. One, it's a polynomial. It's continuous. Bam. Now, some things, like say a square root. Square roots only work where the inside is a positive number. So you remember, think about a graph of a square root. It starts at the location where the inside equals 0 and either swoops to the left or swoops to the right. So it's only continuous on those domain values. So be careful, okay? Is it differentiable? Well, sure, it's differentiable. It's a cubic. It has that perfect, kind of shape. There's nothing that's going to mess up. It's a polynomial again. But let's find the derivative, and let's just take a look at the derivative. The derivative is 3x squared minus 4. That's continuous. There's nothing wrong with that. The original was continuous. The first derivative is. It's never undefined or funky. It really only has to be differentiable on that interval. So like some things like square roots, cube roots, things like that, you have to just be more concerned about what's the domain of that thing. But that's good. Bam, that's good. Now, do the endpoints match? So let's plug in -2 and let's plug in +2. Let's make sure the endpoints match. If you plug in -2 into the original function, -2 gives us -8 plus 8, or 0. If we plug in +2, we get 8 minus 8, which is 0. They match. Because of all the three conditions apply, we are allowed to continue. It was continuous and differentiable on the interval. The endpoints matched. So now we are ready to find the C value. We can even call this over here our C value. The C where it's equal to 0, that is in the interval. I didn't really do that. So let's find f prime of c. So we're going to take our derivative, 3x squared minus 4, and we're going to set it equal to 0. Now, to solve that, there's lots of ways you can factor it, but you got to use square roots. So we're just going to first solve it for x squared, and we're going to use the square root, and then we get 2 radical 3 over 3 when reduced and rationalized. Now, we're only guaranteed one of these values. They might both work. Our interval is -2 to 2. If we do 2 radical 3 divided by 3, it's about 1.15. So that's approximately 1.15, because we have to compare it. Is it in the interval? Well, the positive version, positive 1.15 is in there. Negative 1.15 is in there. So our C values are both of them. Now, again, don't guarantee them that we get 2 of them, but we're guaranteed at least one of them. And the C values here happen to be plus or minus 2 radical 3 over 3. So as you can see, Rawls' theorem is not particularly crazy. It's pretty doable. It's just another way for us to pinpoint some of those critical points, okay? But we're just kind of looking at a particular interval within the function. Now, the mean value theorem is a result of Rawls. It is actually more powerful, and it is the one that is used a little more often than Rawls' theorem. It just says that you'll notice the first 2 things are the same. It's got to be continuous on a closed interval, but differentiable on the open interval. And here it says that there is some C in the open interval where the first derivative is the slope between the 2 ends. The slope between the 2 ends. So here it's just guaranteeing if we connect the 2 ends, if we find the slope of that line, there is somewhere else along that interval where the derivative, the slope of the tangent, matches. So write that down, and then we will look at the little picture over here to the right and see how that works. So this just says that we guarantee that the slope of one of our tangent lines matches the slope that connects the 2 endpoints. So that's the difference. Rawls, the endpoints match. So what's the slope of that line? 0. Here the endpoints may not match. So the slope of the line might be 2, or the slope of the line might be 7. So you're going to say, hey, somewhere the derivative matches that. So let's look at our picture for a moment. So here are our 2 endpoints. The slope between those 2 endpoints is just y2 minus y1 over x2 minus x1. That's just a fancy way of saying that. That's just a slope formula, y2 minus y1 over x2 minus x1. So we have the slope of this line, and all they're saying is that somewhere along that curve, think about it. I'm sorry, see how the slope of the tangent matches. That's all that's saying, okay? Somewhere along the curve, there is a spot where the slope of the tangent matches the slope of the line that connects those 2 points. So now let's apply this to one of our problems. Okay. So it says to verify that the mean value theorem applies. So now we're jumping to the mean value theorem. Okay, so first let's think about the 3 things that we need to think about for the mean value theorem. Okay. The first thing, is it continuous on the interval from 0 to 9? Well, if we draw the square root, you might recall that it looks something like this. Now I'm stopping it and just drawing it from 0 to 9. Okay, so it's continuous there. It's defined there. If they wanted us to use, or if our interval was in the negatives, we would say it doesn't, the mean value theorem doesn't apply. There's nothing over there, okay? So yes, it's continuous. Is it differentiable? Well, if you take a look at that function, there are no pointy points, there's no gaps, there's no holes. So just looking at it, yeah, it's differentiable. But let's think about for the moment what the derivative of this is. The derivative of that is 1/2 x to the negative 1/2, or 1/2 square root of x. That is differentiable here. And that's all that it has to be. Why didn't I have a bracket on the 0? Well, because of the fact that, can you plug in 0 into that derivative? No, because we have a 0 denominator. So yeah, it works, it's fine, okay? So now let's just think about the slope that connects those points. Let's think about the slope between those points. So the slope between 0 and 9 is, y2 minus y1 over x2 minus x1, or f of x2 minus f of x1 over x2 minus x1. That's more function notation. Or f of 9 minus f of 0 over 9 minus 0. Well, f of 9 we know is 3. F of 0 is 0. The slope of that line is 1/3. So what does the mean value theorem state? The mean value theorem states that we're going to find somewhere where the first derivative equals that value. So take and find that value first. Find that 1/3. Then let's set the derivative equal to it. So let's go, where does 1/2 squared x equal 1/3? We already did the derivative, so let's use it. Now that's set up like a proportion. It's very easy to solve if we just cross multiply. So let's cross multiply. We get 3 equals 2 radical x. Let's divide off the 2. 3/2 equals the square root of x. What's going to get rid of our square root? Square both sides. So we get 9/4 equals x. Now the decimal for 9/4 is 2.25. Is 2.25 in that interval from 0 to 9, not including the ends? Yeah. So this is our C. Now let's go back to the graph for a moment. Let's find 2.25, and again, I apologize, my graph is not going to be perfect, but it's pretty good. You can see at 2.25, the slope of that line matches the slope connecting the two endpoints. So that's what that is saying, that there is a spot somewhere where the slope of our tangent matches the slope of the line that connects as the endpoints of our interval. So that's the difference between Rawls and the mean value theorem. In Rawls' theorem, the endpoints have to match. So that means the slope between those 2 points is 0. But the mean value theorem says that if the first two conditions apply, you can match up the slope of some derivative. The tangent slope will match the slope that connects the ends. Okay, so that is the mean value theorem. Let's do an application. Let's do example 416 and how it takes, how we can do that. Okay, it says if a rock is dropped from a height of 100 feet, its position function is given by the one you see there, that s of t. Here's our position function. And then the t is in seconds and the position is in feet. It says first, determine how long it takes before the rock hits the ground. Now let's think about something for a minute. If the rock is hitting the ground, then that means that our height is equal to 0. So don't overthink that spot. If our height position or our position function is given, and if they say when does it hit the ground, just set it equal to 0 and solve. So that's part A. So we're just going to do negative 16t squared plus 100 equals 0. So that's good. And so if we solve that, we get negative 16t squared equals negative 100. T squared equals 100 over 16. Now, I know that's reducible, but because I know I'm going to take a square root, to me, I'm just going to leave it because I can go t is the plus or minus the square root of 100 over 16. The square root of 100 is 10. The square root of 16 is 4. That's plus or minus 5 halves. Now, time is always positive. We're not thinking of going backwards in time. So it would be 5 halves of a second. So at 2.5 seconds, we hit the ground. So that's part A. Don't overthink it. It is what it is. Now, here is where some of our thinking and the mean value theorem starts to come into play. Let's take a look at B. B is find the average velocity of the rock when the rock is released and the rock hits the ground. Okay? Average velocity is the slope between 2 points. So this is just a normal slope. The slope at the beginning it's the slope between the beginning location and ending location. So let's think about our 2 points because we need an x2 and an x1. Well, we know it hits the ground at 5 halves. We're going to call that 2.5. So I know my x2 is 2.5. My x1 is at the start, 0, before I've done anything. So this is going to be 2.5 minus 0. I already did, no, I haven't. Let's do s of 2.5, and let's do s of 0. Let's do our position at the start. That's 100. That one's easy. And our position at 2.5 is easy. That should be 0, right? That's where we hit the ground. Oh, so that was easier than I thought. And then we're just going to do 0 minus 100. 0 minus 100. And so we get negative 100 over 2.5. 100 divided by 2.5 is 40. So the average velocity, is negative 40 feet per second. Now the negative indicates that we are just like we've done when we've done our related rates. If that distance was shrinking, it became negative. We'll think about as it's falling, it's getting closer to the ground. That distance from the top to the ground is shrinking, so that's why it's negative. Okay. Now, it says, find the time guaranteed by the mean value theorem when the instantaneous velocity of the rock is the same as that average. The instantaneous velocity is just the slope of the tangent. So all we're saying for part C is, where does the derivative equal negative 40? So remember, instantaneous is talking about the derivative. Average is just a slope. So the mean value theorem says, connect the slope, find the slope between the two endpoints, and we're guaranteed somewhere where the instantaneous slope of the tangent matches the average slope of the normal line. Okay. So have we done the derivative of this one? We have not. So let's do that. Our derivative, sorry, I keep going to F. Let's make that S prime of C. The derivative, sorry, I keep using different variables. The derivative is negative 32 t plus 0. So we're really just looking, where does negative 32t, the derivative, equal negative 40? Now, we should get a positive time. Two negatives are going to cancel out and get us a positive, which is great. So it's just 40 over 32. They're both divisible by 8. The top 40 is divisible by 8 5 times. 32 is divisible by 8 4 times. So at 1.25 seconds, it's the exact same instantaneous velocity as the average velocity. And if you take a look at the picture, you would see that if you connected the ends and drew that slope, it's the same at that exact same spot at 1.25. So that's basically the mean value theorem and Rawls' theorem. So you have some problems here. In the first set, you're going to do Rawls. So you're going to show me that it is continuous, differentiable, that the endpoints match, and then you get to set the first derivative equal to 0. But for 5 through 11, you're going to show me that it's continuous, differentiable. You're going to find the slope between the two endpoints, and that's what you set the derivative equal to. So that's the difference there, and your answer's over here, so you can check your work. So there you go.